All right. So, anyways, I just said I included the 7.5 notes as a separate file back on Monday's thing. So just make sure you're aware that they're there and present there. And I'm going to open up the one that was already there that has sections 7.3 and 7.4. Really, the bulk of the core problems of this chapter were from the sections that we did already this week. All right? There's really just some small stuff as far as problems left in the book from these last three. That's why I'm going to give you some extra stuff on section 7.5 that's not in the book, only because I've seen questions come up quite a bit on the AP test on that stuff, and your book kind of glosses over that. There's a very short section with not many questions on it. Okay? But before we actually go on, how was everybody on yesterday's lesson if you watched it? Okay, it was basically just taking the same ideas, but also possibly having elastic potential energy involved, right? And the final example we did with the elevator had a little bit of everything. So it could get kind of big and ugly. And as I noted in the video yesterday, and for anybody, for Spencer that was here, was when those, I don't care how you do it as long as you get it right, but when those you get these giant conservation problems that have a bunch of pieces, sometimes it is good to solve parts separately, like this part, whatever, just so you're keeping track of stuff. It could get a little overwhelming plugging everything in all at once into it, but that's up to you how you want to do that. All right, so all that is in section 7.3, and I've actually already used this kind of terminology as we were going through the other section, but we'll just formally define it now since it comes up in your textbook now. Conservative and non-conservative forces. All right, so we now know what the law of conservation of energy is, right? If there's no resistance whatsoever, then only conservative forces are acting on something, okay? Like for a pendulum swinging back and forth, if we could theoretically get rid of all resistance, it should go back and forth forever. So the same, what we actually will eventually refer to in another chapter is amplitude, which is like the height on each side, okay? And that's because the only force acting on this thing, if we ignore any possible air resistance and friction up where I'm holding it, the only force acting on the pendulum is what? Yeah. That's, nope. Just what? What's the only force acting on it right now? Yeah. What's that? Well, I'll give you that there is that, okay? But what makes it, let's go back, let's actually go like this. What makes it swing in the first place? Gravity, right? All right? We can take a circular motion view on it, but kind of ignore that part of it right now. Gravity is a conservative force, though, okay? And what does that mean? What it says up here, just the definition. It's a force that can offer a two-way conversion between kinetic and potential energies. Isn't that what's happening here, right? It pulls it down, but its own inertia, once it gets to the bottom, takes it up to the other side. And there is a centripetal force there, which is making it hang on the system in the first place, okay? But we'll not worry about that right now. And that's why for a swinging pendulum, we just transfer from one side to the other, kinetic to potential, right? At the lowest position, it's all what? Kinetic as it passes through, because it can't get any lower, assuming this can't break, right? So gravitation, from what we've been using and studying, conservative forces that we've seen already are gravitational force and the spring force. Because when I take a spring pendulum, which I have a simulation of right here, I just have it in slow motion. A spring pendulum is just a mass hanging vertically on a spring. We will study these and other pendulums in a lot more detail in the final chapter of the year. We're studying their energies now, but there's a lot of stuff other than their energies to study that we'll get in a chapter called Simple Harmonic Motion. But I just have this one going in very slow motion. I don't know if I could put friction on it. let me reset it for a second. Okay, so right now, this spring's at its natural equilibrium position. It's not stretched or compressed, right? But when I put a mass on it and pull it, stretch it into motion, now I give it, by stretching it, I give it some elastic potential, right? And actually, since it's moving up and down, a mass hanging vertically also will change gravitational potentials, right? But anyways, make it go a little bit better, and I'll slow it down again. But just like the string pendulum going back and forth, this transfers from potential to kinetic, right? At some positions, it's moving faster. At some positions, it comes to a full stop, right, before it changes direction. All right. But during this, again, if there were zero resistances, it should just bob up and down forever. It doesn't, but if theoretically, if we could get rid of any resistance, and that includes on a spring even own internal resistances, because the materials of the spring stretch itself out, there's internal friction in the spring, which basically is impossible to get rid of, otherwise you wouldn't have a spring anymore, right? But theoretically, if that was ignored, and it would just go up and down forever. And one other little thing, actually, that just popped into my head that it's a little bit important. When we studied Hooke's law for the first time, the last chapter, and I brought it up again yesterday, what was Hooke's law of the equation? F equals little equation. It's to find the force of a spring stretched, or anything elastic stretched or compressed. Yeah. F equals kx, which k was that value called the spring constant, and x was just the position or the displacement stretched or compressed away from equilibrium, rest position. Okay? And one thing to note, because I don't think I said this yesterday, Hooke's law is good as long as you don't overstretch a spring. If you overstretch a spring, then you could deform it, and it changes its spring constant value out of whatever constant it was, and it damages the spring. So as long as you don't have really big stretches, or in some cases, if it's a compressible one, it can happen that way, I guess, as well, but especially for stretching a spring. If you overstretch it, you'll basically bend the coils and deform them, and then Hooke's law is no longer applicable, because that will mess up the force constant or whatever it was, and the springiness of the spring. That's not a technical term, by the way. All right, so anyways, conservative forces, not to spend too much time on this, is just forces where the work is always reversible. That's why it's conservative, all right? If you drop something, even if it's a pendulum or just a ball, I could get all that energy or work back by picking it back up to here. And now I have the same potential energy easily. I could get it back easily. I could do something, some kind of work to make it reversible to get all that back easily. And also, just a note here, work is independent of the path, only depends on the starting and ending points. Okay? And with that in mind, and Spencer out there and Brendan, I'm going to have to show you guys this. I can't really position my camera well to go to the back of the room. So the example I'm going to do here, I'll show it again when I see you guys again, because it's a quick one. But this is in general with work and energy. You guys might remember the other day, I don't know if it was yesterday or the day before, I noted that some of the problems we would do in this chapter might seem like problems we could have solved other ways. We're using energy. But energy is nice. Work and energy methods are nice because they are scalar products. Or they're scalar values, I should say. And that means they don't care about what direction. Again, I've said this a million times, but it's important. Positive and negatives on work or energy, this means gains or losses to the system. So a quick question here. If you can't see, you can move to see better back here. I stole this off one of my kids years ago. So anyways, I have two tracks set up here, right? They look very different from one another, right? If I roll a ball down each track, which one, the one on my left or the one on my right, This one's the left. Which one will the ball be moving faster at the bottom when it gets to the floor? All the same? Any other guess? Answers? How many say all the same? How many say the one on my right's going to go faster? How many say the one on my left's going to go faster? Alright. Well, I don't have anything to 100% prove it because I don't have like a radar gun at the bottom of this thing. However, what Z said's right. Alright? Whether I roll it down this path, you catch that when it gets to you, or this path, when it gets to the bottom, I know you can't really verify it with just your eyes, but now take my word for this. It would be going the same exact speed once it gets down onto the flat ground. Why? Hey. Exactly. The vertical distance is what matters. Just like that note up there says, it's independent of path. Only depends on the starting and ending points. Don't these have the same starting and ending points, especially vertically for gravity? Gravity works on the vertical axis, right? So we would say in terms of what we've been learning that on either one of these tracks, this ball has the same potential energy, right? And therefore, if it goes down to the floor being the reference level, that's where it gets to in the end. Now it does different things from in between, but we're not asking in between, right? We're asking beginning to end. And since they both start from the same height, it ends up being the same. Now, there is a stipulation on this, we gotta say, that it would, with absolutely no other outside significant forces. This is a steel ball bearing, and this is plastic that's fairly hard. And there's very little what while this thing rolls. Friction. However, if I slid something down this track that didn't roll, that still made it to the end, that had significant friction, would they have the same speed at the end? No, because this path is clearly longer, right? If we stretched it out straight, there would be a lot more path for friction to occur, right? To rub, so it got down to the bottom. And a lot less on this one. So if there's significant resistance, then no, they wouldn't be going the same at the bottom. However, if it's not, if it's pretty negligible, which would be here for this hard rolling object and another fairly hard surface, then it's all dependent on the initial gravitational potential energy. All right, non-conservative forces. So as I just said, friction's a non-conservative force. And the main reason, easiest way to kind of identify a non-conservative force is it would be hard to get back the work done by this. Like on a spring or a spring that's stretchable or compressible. If I stretch it and let it go and want to get that back, I do work on it and pull it right back and get it back to where it was, just like I could lift the ball up and do that, right? But with friction, and we noted this a little bit the other day, that what does friction create? Yeah, heat and through that process sound, right? And heat and sound dissipate, not disappear, but dissipate into the air around it, basically. And it's not like when I'm done with that, I could be like, oh, I'm going to grab all that energy back that dissipated around it. It's not like a spring, or it's not like what we could do to lift something up to get that gravitational potential energy back. So I've noted there the dissipation. And friction, I noted back here on these tracks, it does depend on path, right? Those two paths vertically were the same on the vertical axis, but the literally stretched out length of the track, the longer one would have more friction if it was significant. All right, so friction's our good example of a non-conservative force. It's usually in mechanical physics the most common non-conservative force we run into. And that's it with section 7.3. It's just defining those terms and what they mean. All right, so 7.4, I'm not going to 100% prove this formula, but we'll break it down a little bit more in the one activity we're going to do on the website today. It's just going to be presented here. But to fully prove this formula, it involves integration, which I believe you still didn't get to in calculus, right? So I'm not going to talk about something you haven't got to there. But the outcome is what's important, all right? The force from potential energy, if we want to find it, is equal to the derivative of a potential energy function. So if we have a potential energy function, like a u of x function, the potential energy, I'm going to show you some real ones here in a second, because it'll make this make a lot more sense. But we have some graph, some function with potential energy on the y-axis, and its position at any given moment on the x-axis. That could be a horizontal position. It could be a vertical position. We could have u of y functions, and it would be the same thing. Some axis that we're focusing on, as it moves on that axis, what's happening to its potential energy. All right. We could have two-dimensional or three-dimensional things as well, and we'll break down how that works. It's just piecing up the formula. But the main thing is, if we have a potential energy function, a function of potential energy with displacement on some axis, if we take not just the derivative of it, but the negative derivative, then that gives us the force at any given moment. That is the force from that potential energy. What could that force be? It might be gravity, because gravity is a conservative force that causes changes in potential energy, right? It could be the force of a spring if we're looking at a spring and its potential energy as it flows, okay? So, why is it negative, okay, is the question. And I'll use a simulation. That's pretty bad. I have something that says looks at the graphs on page 7.22, but we're going to see some simulated graphs here that are probably even better. All right, so let me go to one of the simulations again. It's all actually due to something we already talked about. All right, right now, we used this simulation earlier this week. Right now, this simulation is at equilibrium. There's no applied force on it. This spring is at its equilibrium position. All right. To give it potential energy, it has none right now. Right? It's not stretched or compressed. To give it potential energy, I would have to either push or pull on it. Right? I would have to either compress it or stretch it. And again, one way to find the force would be Hooke's law, but maybe we don't have the information to use simple Hooke's law for the force. But maybe we have a graph or a function of potential energy, like a u of x function. All right. So let's say I stretch this thing, and I have vectors on here. If I pull to the right, the orange vector, where does the spring pull on me? Opposite, right? If I'm pulling to the right, where does the spring want to pull? To the left, where the blue vector is. They're the same magnitude in any given moment when I stop or pass through, right? But they're different directions. Again, I related that to kind of a Newton's third law thing when we first saw that earlier this week, or yesterday, I think it was, when we used this on the video. That essentially, well, hopefully explains to you why this force represents the force of the, like in that circumstance, like the spring pulling back, all right? And it pulls back to try to get back to equilibrium. That's why we include the negative on the derivative, basically, because it being what we might call a restoring force, trying to get it back to equilibrium. And this would be a conservative force because it's a force of a spring, right? But we could also show this, and we'll show it with gravity being like the potential energy involved with the potential energy function. But I made a little note here. A conservative force, like this force on this spring, is always trying to pull or push, depending on if you stretched or compressed it. It always tries to come back to equilibrium unless you overstretch it. All right? But gravity does the same thing. When I lift the ball up and drop it, what does gravity try to do? Pull it towards lower potential energy, right? As you fall, you get less and less potential energy. All right? So in the end, the main point of this little section is that if I give you either a graph of it or an actual function, if you take the negative derivative at any moment, that gives you the force from the potential energy. All right. Usually we're only going to have to apply this on one axis, but you could have multiple dimension things. If you have functions that you'll see in a quick example we'll do here in a second, if you have multiple dimensions of motion, you could just apply each axis this idea separately, basically, x, y, and if there is a z, z. This is not the most important thing, but it's in the book, so I put it there. If you kind of view that on all axes if they're present, this big ugly turn of taking the derivative in unit vector notation on each separate axis of the function, with respect to x, then with respect to y if it's there, and respect to z if it's there separately, still have the negative out there for reasons we talked about to begin with. This whole thing is known as sometimes known as the gradient. It's just, I guess since it's big and ugly, they came up with a symbol that makes it. And it's actually an upside down triangle, not a delta, right? But honestly, that's not that important. So I'm not going to say much more about it. What's important is just applying the simple idea. So go to page 7.1, or no, page 223 and find example 7.14. I mean, if you could do a basic derivative, this is a pretty easy example to apply this on. It's just knowing that you're supposed to do it and remembering that, okay? All right. Now, it doesn't really go into a whole lot of detail about the system in this example, so I don't love it. But this is to give us a formula. We don't really have to question how this system's set up, but it's got to be, it says a puck with coordinates x and y slides on a level frictionless air hockey table. So an air hockey table is flat, right? So the x and y axes must be two-dimensional. It's just basically telling me this puck, whatever's acting on it, to move it. We're not sure what is. It doesn't tell us. But whatever it is, we could think of the plane as an xy axis on the plane, like laying down. Not like this, all right? It's not going up and down from it. It's just two dimensions on a flat surface. So it's going to move not in a straight line, but like an air hockey puck might move on a table. It's going to move possibly different ways like this, right? Okay? So that's the kind of picture we have to take of why this is in two dimensions. All right, it's acted upon by some conservative force. We don't know what that conservative force is. But we know the potential energy function is given as this. And it is a two-dimensional function because it has x's and y's in it, right? So if you ever apply, well, let's go on to what it says. I don't even think we need to know. Hold on, let me remember something here. I don't remember why it tells us this. It says, note that r equals square root of x squared plus y squared is the distance on the table surface from the puck to the origin. I'm not really sure why they told us that because it's not really needed. Maybe just FYI. The main thing is that it says find a vector expression for the force acting on the puck and find an expression for the magnitude of the puck. Okay. I realize why. It's just reminding us that the resultant in two dimensions you use the Pythagorean theorem for. We should already know that. Okay? We'll see in the end if you don't recall. All right. So basically, potential energy function, find the force. Let's just cut it down to that. That's really all that matters. But since there's two dimensions, I'm going to find it separately with respect to the term that has x in it and separately with the term that has y in it. That's what all this is telling me I'm allowed to do, basically. So the number one thing I'm going to do is actually just quickly distribute the 1/2 through the x squared and the y squared. So I get two full terms right here, right? So first, if I take this whole thing, this whole function right here, and take its negative derivative with respect to the x-axis, or the x-coordinates, this term has no x's, right? Correct? Therefore, in the eyes of taking the derivative with respect to x only, this would be a constant, wouldn't it? Does that make sense? So therefore, that disappears when doing this part of it. And then we just got a simple power rule here, right? Do the power rule. 2 comes down, cancels the 1 with the 1/2. Remember, we're doing the negative derivative because of the restoring force thing. And negative kx. Easy derivative, right? Then we apply separately to that function with respect to y. And then the opposite happens. If I take the derivative with respect to the y value, y quantities, then this piece is a constant, right? It goes away, and I get a similar looking thing with the power rule on this one. All right? So we've achieved what it said, first of all, is finding that. But it did say find an expression for the magnitude. That means of the overall force. What we just found here are expressions for the x component and y component separately, right? So what do we do if we have components and we want to find an overall magnitude? We put them into the Pythagorean theorem, right? And we run them, and if we do that, we could make it look prettier. We could factor out the k out of the square root and have something that looks like this. All right? But of all this, what matters the most, I don't want you, because there's not going to be, like, I'm not going to say there's not going to be a question like this on the test. There will be, but it's minimal stuff compared to, like, all the other stuff we did in the chapter right now. So the core thing to remember is if you got a potential energy function, if you want the force, you take the negative derivative of that function. All right, and we're going to visualize this better in a second with some things in section 7.5. So the part of the notes that I included, I just restated what we just learned. It's important to remember this, the fact of what we just said by what taking that negative derivative gives us. We're going to now look at actually like what a function graphically looks like. The best way to understand anything functionally and calculus-wise, to make full sense of it, like I've always said since the beginning of years, understand it graphically. So there's a simulation we're just going to look at real quick that just went away. That's nice. Let me reload it, see what happens. Oh, I was literally just messing with this before. There you go. Before you guys came in. All right, I'm going to get rid of things that don't matter right now. We don't care about time graphs right now. That'll come later in the year when we study pendulums more closely for other reasons. I don't care about that one. And I'm going to slow it down to a slow speed. All right. You're going to see 2 graphs. Actually, they're already made. But what I'm going to do in a moment is hit run, and this thing's going to oscillate back and forth. It's going to be compressed. Obviously, it wouldn't magically start by itself. So it's like imagine somebody takes this block on the horizontal, pushes it, and lets it go. And then what it will start doing? Back and forth, right? It would go, if there's no what, it would go back and forth forever. Friction on the surface, and if there were no internal resistances on the spring, theoretically, it would go back and forth forever. So on this particular simulation, it does ignore all resistances and non-conservative forces and do what it would do if there were only the conservative force of the spring on it. So I'm going to hit run. And don't focus on the green one right now. Focus on the red one that has a U on it, because we're focused on potential energy right now. So this dot is just following the exact position where we are on the graph. It would make a U like a bowl shape, wouldn't it? Because I'm going to pause it here in a second when it gets back to the most compressed side. Again, ignore the green function for now. I can't turn that one off. It'll be important in a second. But let me pause it right there. Right about there is its maximum compressed potential energy, right? And this is the y-axis. This is the x-axis of our graph. And on, vertically speaking, which would be the gravitational potential energy U on this axis, the energy axis, as it points here, it has its most at that position. That's why they drew a line right there. And I'll get to why it says mechanical energy there, but you already probably know from earlier in the week. All right, so whatever, it doesn't use exact values here, but whatever amount of gravitational energy we have right there, at that position, what's its kinetic energy? 0. And now we can see that from that graph, right? It's down the whole way. So whatever amount of potential it has right there, elastic potential, I think I said gravitational, this is elastic. Whatever amount it has right there is the total mechanical energy, right? Because remember, mechanical energy is at any given moment the total of potential and kinetic. If there's no kinetic, all the mechanical energy at that moment is due to that. And we are to where I started from before I hit run was the equilibrium position. It wasn't moving, right? So notice I go to the left, right? So I'm in like the negative positions right now, right? If we're measuring from right here was marked x equals 0, it's now pushed back to some negative x max. Later in the year, we refer to that as the amplitude, okay, of something like this. And then I'm going to keep letting it run, and it will pass through the equilibrium position in motion, not stop there, but once we pass through, it begins to stretch. And now we get to the other side, the maximum positive horizontal displacement away from equilibrium, where again it stops for a moment, right? Because that's when it turns around. The spring is stretched as much as it's going to it is able to pull it back. So it's simple, as long as there's as long as we're ignoring any crazy non-conservative forces, actually even if they were there, it would look like a mu, to be honest with you, or not a mu, a U-shaped graph for this particular thing. And it would just travel back and forth. And what's nice about this graph, you could see physically as it goes, that for every joule of energy gained or lost by potential, it's gained or lost by kinetic, right? And that's showing really conservation. All right, but let's pretend for a minute, just remembering the ideas of calculus, all right, graphically, is what's really important right now. So this red graph is that potential energy position function. And if we wanted the force, we would take the what of it? What did we just learn? What did the equation just say? If we wanted the force of this function, we would need to take the what? Negative derivative. Graphically speaking, what is a derivative on a graph? What kind of line? Don't forget this. Sometimes you just keep using all these rules of derivatives and forget what it means graphically. Yeah, the tangent, right? So if I drew at any position, where my dot at any certain position, let me get in a certain one here. Let's say right here. Oh, I didn't pause. Right here is fine. If I wanted the force right here, it would equal the whatever the tangent line to the curve is right there, right? We can at least mark it there. We don't know what this actual function is. It's not written, whatever. But the concept is what matters here. So let me run it to an exact position I want it on and ask you guys something. Right about here, or close to there. I'm close enough. What is the derivative of that position? What kind of line do you get from the tangent line? Because remember, the derivative is the slope of the tangent line, right? At that position of this graph, what kind of line would be tangent right there? Flat, correct? What's the slope of a flat line? 0. So that would be known as, on the graph, the equilibrium position. The equilibrium positions on the graph are where force equals what? 0. And notice, that's why I picked this simulation as a pretty good one, because it shows the graph and exactly where this thing is at the same time. Where does this happen to be right now? This spring is at the equilibrium position, right? So when it passes through any equilibrium positions, then that means there's got to be a flat line for this tangent line at this, for the slope of the tangent line at the position. Because that's what we define as the equilibrium position. We want to make all those little connections. Does that make sense to everybody? Okay. All right, I'm going to use this. So that was an example of this. And there's two types of equilibrium I have on the notes we'll get to in a second here. I'm going to use a different simulation that involves not springs, but just simple like a track with a dog on it for some reason. All right. So in the notes, I have a graph that looks almost just like that track because I'm going to use that track to refer to these notes with. Okay. In a situation of like a roller coaster track or like a skate park board track like that or whatever, be careful. This is a graph that looks just like that track, right? It's a graph of potential energy with horizontal displacement, not vertical. I know he is displacing vertically, but that's not what this graph represents. I'm graphing the potential energy. It literally goes right along with the track, right? Because what happens when the track goes down? You lose potential energy, right? When the track makes you come up, you gain. And yes, he is moving up and down, but as he's going along this track, he's also going along the x-axis. So this function is a u of x function, not a u of y function, all right? So with that in mind, let's go back to it. And again, I have all resistances off right now. And I'm going to pause it at certain spots. Right at the bottom, it's hard. Well, I don't know if, oh yeah, let me go slow here so I can pause it more easily. Let's go. I'm going to get it right at one of these certain positions. And stop. Good. That's good. Okay. So right at that moment, if this track basically is the u of x graph, at that moment, the derivative is what of this function? Yeah, 0. All right, so therefore the force is what there? 0. What is the conservative force involved here? Not a spring, but what? Gravity, right? And that should hopefully make sense. The force of gravity doesn't disappear, but it can't affect my potential energy directly at that moment, basically. All right, because the track is directly underneath me, right? So since the track's directly underneath me, that's basically why that's occurring there. I'll let you guys have a break in 1 second. There's 3 positions where that occurs. I guess I don't have to stop it there. Here, here, and here are all positions where we'd have a derivative equal to 0, right? So there's 3 equilibrium positions here. Going back to the notes, we call the ones that are in, like, let's just call this a valley, a dip, right? The ones that are in a valley are known as stable equilibrium. So on this particular example, there's a stable equilibrium position here and here. This one's considered unstable equilibrium. They're all equilibrium because of the fact, as we keep saying, I noted over here, the derivative of those positions are 0. But why do we call it stable versus unstable? Well, really because of if I just grab this thing, especially if I put resistances on. Let me put some friction on. If I'm in a dip or a valley, and I let this thing go, eventually it's going to come to a stop. So that means we position it in a stable place where it'll, with resistances, if they're present, will settle it down and eventually stop, right? Or even if there's not resistances present, it will stay in that valley, won't it? And it will just go back and forth to some maximum height on each side, but keep rotating through it, right? That's considered stability on one of these graphs. But if I take this dog and I put it right here, if I nudge it, if it moves a little bit to the right or the middle, if we start here and we move a little right or a little left, we fall off, don't we? One way or the other. And that makes it why it's considered unstable equilibrium. Does that kind of make sense? But that's a very simple thing. Mathematically speaking, did you learn yet for any reason like maximum local maxes and local mins of graphs, right? So at maxes, local maxes, those are unstable positions of equilibrium. At local mins, those are unstable positions. And it's as simple as that. So there's been in the past on the AP test some simple questions about that in the multiple choice. And it's a real simple idea if you just understand where they are. Okay? All right. One other little thing that doesn't necessarily pertain directly to this section, but I mentioned earlier in the week, on this particular simulation, since I could show it, I will. Remember, in most cases, unless we got a lot of crazy stuff going on, which we have had in some problems throughout the week, in most cases, like, where's the most sensible place to put the reference level to measure potential energy? At the lowest point, right? Like on the ground right here, right where the lowest dip is, right? And that's where it's naturally set at. But this simulation actually allows me to change the potential energy as well. So right now the dog's on that one. If for some reason I needed to, I could reposition the reference level like up here. Why? I don't know, but I could, right? Notice what happened to the potential energy when I did that. It's now what kind of potential energy? Negative, going to the bar chart it's underneath, right? So just wanted to show that again. It doesn't really matter. It doesn't change anything about what's happening. It's just how your view of what's happening changes when you set your reference level at different positions. All right. If I hit play right there with the reference level up there, the kinetic energy bar, let me start it from the top, does the same things that it would have if I dropped it from the top wherever the reference level is. Because the formula for kinetic energy is 1/2 mv squared, right? The formula doesn't care about where a reference level is, right? But for potential energy, it does, all right? But that does affect the total mechanical because you're just viewing it differently. I just wanted to show that very quickly. All right. If you need to take a quick break, I know the bell rang, but since I held you, if you need to, you can. And I've presented all the ideas. Now we'll go into some other questions, but I'll wait a few minutes.